So earlier today, or this morning, I ended up at the beginning of what I was calling the equivalence theorem. That's the general name. And this is the proof that if you have two operators that satisfy a relation like this linear combination, which vanishes when the equations of motion are applied, if that should happen, then what the theorem shows is that the S matrix depends only on this linear combination of coefficients. And instead of going straight away to the field theory part, then I will go and do an example in quantum mechanics, which I think might motivate the thing. All right, the example is straightforward. So what the theorem says, I should say, the theorem says then that if we have an object that looks exactly like this, a phi like this is an operator. If we have an operator that looks exactly like this, then it should have no effects at all. This is an equivalent, sorry, well, this is an equivalent statement of the equivalence theorem. So if you have an operator like this is an operator, the same dimension as O and O prime, and this operator you put into your effective theory, this operator will have no effect. That means this S matrix will have no dependence on the coefficient of this operator. It will be independent. And that's what I'm going to look at. So this is my theory. It's a very simple non-relativistic quantum mechanics in one dimension. The x is the coordinate. And what I'm adding to it is a term that vanishes on shell. And on shell is exactly the definition that I just gave you, that vanishes when the equations of motion are obeyed. And I'm using more or less the same notation. A represents this curly A, and this variation here in one dimension quantum mechanics, in one dimensional theory, is exactly this. You derive this from this. One can easily rewrite this by making an integration by parts in this part, so that the Lagrangian depends only on the velocities and not on the accelerations. And you get this. The momentum, the canonical momentum, you get by taking the standard expression, taking a derivative of L with respect to x dot, and it's this object that again depends on the effective operator that I added. And I forgot to mention, so I introduced an expansion parameter. I mentioned that I'm working to leading order. In this case, it means leading order in epsilon. This corresponds to 1 over lambda squared expansion, and this would represent these terms would represent the higher terms in the effective theory. I take this, and using this expression, I can construct the Hamiltonian. This is the standard expression of the Hamiltonian, and if you work it out, you get this object. This is the standard thing you would get from this Lagrangian immediately. It's straightforward. And this is an extra piece that comes from adding this extra piece. And I will call this extra piece H prime. I'll call this thing H naught. Now, if I want to quantize the theory, I can, of course. The only subtlety occurs on this term because of an ordering problem. If A depends on X, and so whether you have A prime PP or you have PA prime P or PPA prime, quantum mechanically as operators is different. So what I will do is choose an ordering so that the operator, the Hamiltonian is Hermitian. I will just impose that, I will choose that ordering, which is equivalent to doing this. The curly brackets denote anti-commutator, or equivalent, this is the symmetric ordering with all possibilities. P squared A prime, P A prime P, A prime P squared. And if you substitute this thing that I had here in here, well, you get an expression for h prime as an operator, which is here in the parentheses. And what is interesting is that this full expression for h is just a unitary transform of h naught. So there's a unitary matrix explicitly presented here, that if you calculate this thing to order epsilon, you get exactly this. So this is an identity. An identity. I remind you that thing in here, the p squared plus v, is what I call h naught. And then when you dagger at this thing, it's a unitary transformation. So the theory is unitarily equivalent. The theory with this is unitarily equivalent to the original theory. So the theory with this Hamiltonian, corresponding to the Lagrangian with an epsilon term, is equivalent to the original Hamiltonian because unitary transformations are free for you to do. And it is in this sense that an operator that vanishes on shell in a quantum theory, it has no observable effects. You can make a unitary rotation, and then all the effects of this term in the Lagrangian or the Hamiltonian disappear, and you're back with what you had when it was not introduced. What does change are the canonical coordinates, okay, like this, and you can work out all observables. But that's basically at this level the equivalence theorem. Right? We added a modification that looks highly, or can be highly non-trivial to the Lagrangian, and yet by virtue of its vanishing on shell, it is in fact an unphysical modification, and an observable modification. Any questions about this example? Doing this exact same procedure at the quantum field theory level is not feasible. Well, certainly it's feasible. It's just it requires too much background material. I would have to introduce the Schrodinger picture in quantum field theory, which is doable, done, but it's very, very rarely taught. So you're very unlikely to be familiar with it. And so I will not go through the same, I will not follow the same approach when I do quantum field theory. But I did want to bring it up because this is what's going on. We added a term, and we can eliminate it by doing an appropriate unitary transformation. If you want to do the classical theory, that's perfectly okay. The only difference is that instead of doing a unitary transformation, you do a canonical transformation. An appropriate canonical transformation will get rid of this thing. And the generator for such a canonical transformation is essentially this object, P times A. Well, then let me move on to the quantum part, quantum field theory part. I'm not going to worry about, okay, I will sketch the proof. I don't want to go into painstaking detail about all possible issues with divergences and so on, but I will mention as I go along the main pitfalls that you might encounter. So I'm going to go back and look at my effective theory, and now again we have two operators that to leading order are related by the expression that I had before, and that unfortunately I did not write down here. So these two operators, O and O prime, are related by this expression here at the bottom. So let me put it on the board. All right. The idea is to put your theory inside a functional integral and then to do a change of variables, or what's often called the field redefinition of this form. I shift the field by the expansion parameter 1 over lambda squared, if you wish, C prime. I'm going to, okay, so what I'm looking forward to is getting rid of O prime. And I can do exactly the same approach and get rid of O, but I will do the O prime. And so E C prime times A, and A is this A here, okay? Then if you do this transformation upon the Lagrangian that you have originally, you get this expression here. And I note that I've chosen this coefficient cleverly enough so that this combination right here, by definition, can be written in terms of O. So you have this expression O. And you may say, well, now I'm done. I'm done. You just made a change of variables. Then with the new variables, then you have shown that the effective Lagrangian doesn't depend on C and C prime separately, but only on this linear combination. We're done. But it's not quite the case. There is a little bit of subtlety, because whenever you make a change of variables, you have a Jacobian in the functional integral. And here it is. You have to change the measure by Jacobian. The Jacobian is the determinant of the variation of the, you vary this with respect to phi, and you take the determinant of that, and that's your Jacobian. Okay, great. And I'm working to order epsilon, and so you get determinant of 1 that comes from the variation of this guy, and then a variation of A. And you have 1 plus something, and I'm going to work to a leading order in epsilon, and so the determinant of 1 plus small is equal to 1 plus trace of small, which is this. And I will call this the Jacobian, okay? Now, if you notice, everything here, the operators I've been telling you, are local. They depend on the field at one point, or the derivatives of the field at one point. This is local, this is local, this is local, and therefore the curly A is local. It depends on phi and the derivatives of phi at one and the same point. So when you take this variation, you find immediately that this is full of derivatives or of delta function, or the delta function itself, evaluated at 0. But you are fearless quantum field theory practitioners, and you know that what you have to do is, before you throw up your arms in despair and leave the room, that you have to regularize things. And which regularization you use, well, it's up to you. But if you decide to use dimensional regularization, what happens in it is that this type of divergent objects is 0, regularized to 0. And that's okay. But what if you don't like to use dimensional regularization and really uncomfortable about these things? Well, that is also okay, because in general what you find is that the things that multiply this delta to the 4, the objects that multiply this this operator. So for example, A can have a term that's polynomial in phi, say phi to the n. When you take a derivative of this like this and take the trace, what you get is a delta of 0 times phi to the n minus 1. Okay. By the construction, and that's not something I'm going to prove, what happens in this calculation when you don't use dimensional regularization is that the thing that multiplies the object involving the fields and its derivatives that multiplies delta function at 0 and so on, they are all or can be absorbed in renormalizing the coefficients of the light theory. So they are renormalization effects. But if you use dimensional regularization, you don't even have to worry about it to begin with. All right. So the Lagrangian depends only on this thing. I've swept, as we do in renormalization, the divergences that show up here under the rug, and there's one thing left over. And that is where part of the physics comes up. When you do a functional integral approach to finding all the correlators that you're interested in, you end up with a generating function that depends on some current that I'm going to call eta. That's a current eta. And you have an expression like this, e to the is, and then you add a source term, eta phi, so that whenever you want to, to obtain a correlator, well, you just take derivatives of zeta with respect to this external source, and then eventually set the source to 0. So in the expressions that I've told you, I've dealt with this guy. Concerning this guy, I've shown that it depends only on the combination C plus AC prime. But what I have not done yet is talk about what happens to the source. When I replace the field like this, there's the field like this, then I have to do it everywhere. So now I have plus epsilon C prime A here. And you say, well, okay, fine. So now when I take derivatives with respect to eta, it doesn't bring only a factor of phi, but brings a factor of phi plus unwelcome friends. But in fact, those unwelcome friends are harmless whenever you calculate S-matrix elements. The reason for that is that there are two possibilities. One is that A has a term or more terms that are linear in the fields. I'll come to that in a second. But there's another possibility that A has more terms that have more than one field in it. Phi squared, phi cubed, phi d mu phi, phi box phi, whatever it is. Those terms are harmless when you calculate the S-matrix elements, because I remind you, to calculate the S-matrix, you take your favorite diagram, you get all the external propagators, then you ruthlessly amputate them by multiplying by the inverse propagator, and then you set every single external line on shell. If you have an external leg, that's what happens when you bring down this factor, including an A. So if A has more than one field, the external leg corresponds to more than one field. And so it will have no single particle pole. When you multiply by p squared minus m squared, the inverse propagator, the amputation, it doesn't cancel anything in the denominator. There's no such thing in the denominator because there's no single particle pole in A. And so when you set the external legs on shell, those terms vanish. And that is why this is the dependence, that's the dependence of the theory only on shell, only for the S matrix, only for observables. If you don't do that, you just calculate the endpoint correlator, which is something you can calculate, then the dependence on C prime does not disappear. You know, you bring down n powers of this object over here, and there will be n phi's, and there will be at least one inclusion of A multiplied by C prime without the C, independent of C. But those terms, the ones that depend on C prime by itself, disappear on shell. And there's one last remaining point. It's when A has a single particle pole that is linear in phi, or has a term that is linear in phi. So you have 1 plus epsilon C prime phi, the whole thing, 1 plus epsilon C prime times phi. That case is also not problematic because the factor 1 plus epsilon C prime can be absorbed in a wave function renormalization. And with that, it's a long story, but I tried to be as precise as I could, then the theorem is, I wouldn't say proved, but I hoped argued convincingly for. 3 steps then. Make a field redefinition or a change of variables. In that case, this piece, the S, is shown to depend only on this linear combination. Any effects from the Jacobian, renormalization effects, any effects from the shift in the sources can be absorbed either in the renormalization transformation or are irrelevant for the purposes of calculating the S matrix because they don't generate single particle poles. And that is the equivalence theorem. Okay. Any questions? Okay, so let me go on and try to provide an illustration. Of course, I provided an example of how that works. I'm going to work it out also here. And you in the back cannot see this, right? Am I right? Okay. Okay, so I hope you can see this. All right, excellent. I am going to look at an example of the phi to the 4 theory. This squiggle here is intended to be a 4. So this is not like one exclamation mark, but it means 4 factorial. Okay, so this object here is 24. This object here is 2. So it's 1/2 d phi squared minus 1/2 m squared phi squared minus 1 over 24 lambda phi to the 4th. My symmetries. I have a Z2 symmetry. I want the light symmetries that the theory is going to be invariant with phi goes to minus phi. That's why I don't have a phi cubed term here. And Lorentz invariant. That's it. Those are my light symmetries. I only have one field. And so the operators are of the form 2 to the n, 2k, and the dimension is n plus k, actually 2n plus 2 times n plus k. I forgot the 2 here. The smallest dimension that is not included is relevant. Dimension operators correspond to n plus k equal to 3. And that is dimension 6. I'm sorry, I missed a factor of 2 here. This should be 2 times n plus k. So the smallest dimensional operator corresponds to n plus k equal to 3. And here they are. And what I'm going to show is that all dimension 6 operators are equivalent to phi to the 6. And so this is just a more careful presentation than the one I did earlier today. Okay. So these are the operators that I have. These are the equation of motion. The equation of motion. And so for example, I can write this operator like this. What I mean by this plus EOM is the following, that if I transpose, this squiggle here is a 3. So if I transpose this to the left-hand side, you get 5q times box plus m squared phi plus 1/6 lambda phi cubed, which is phi cubed times the equation of motion. So the difference between this guy and this guy is a term proportional to the equation of motion. That's what this EOM means. EOM means a term like this here on the board. And so what does the equivalence theorem say? Well, the equivalence theorem says that I can replace this operator in the effective theory by this guy. And this guy has two terms. One of them is minus 1/6 lambda phi to the 6, here it is. And the other is a term that's phi to the 4 m squared. So the effective Lagrangian will have, if you replace this, c prime over lambda squared times this, plus c prime over lambda squared times minus m squared 5/4. The last term, and once proportional to m to the 4th, can be absorbed in a finite renormalization of lambda. So instead of lambda, I have lambda minus m squared over capital lambda squared phi to the c prime. And so the equivalence theorem tells me that the effects of this guy and the effects of this guy are the same. You can do exactly the same thing for the other guy, this. In this case, you can show, I'm not going to go through this thing, you can do the same, play the same game, that this is the same, can be replaced by lambda squared over 36 phi to the 6, plus terms that vanish when the equations of motion are imposed, plus a renormalization of both lambda and m squared. So when you do the same trick of replacing boxes by this type of object, then you end up on the right-hand side with terms that go like phi to the 6, which is this, terms that go like phi to the 4th, which are eaten up by renormalizing lambda, and terms that go like phi squared, that are eaten up in renormalizing m squared. And so what we're saying is, what this is saying is that the theory, the underlying theory, cannot differentiate between the two operators, box phi squared and box phi times phi cubed, and the phi to the 6 operator. So the most general, leading in 1 over lambda, effective theory is right before your eyes. Just one unknown coefficient instead of 3. On the one hand, you say, well, 1 to 3 is not a big reduction. But on the other hand, if you decrease by 33%, to 33% of the original number of unknown coefficients, it's very nice. So instead of having to make 3 measurements to see if you have new physics, you only have to make 1 measurement. Any questions about this? This is intended to be a straightforward calculation, but I'm prejudiced. Questions? Yes?
So, hello. Effective operator can never be equivalent to the low energy any other operator, right?
Well, at low energy, these are equivalent. But
No, the theorem is for 2 effective operators, right?
Yes.
One of them being effective and the other one being
ineffective.
Right.
Exactly. So what I'm saying is, it is the only thing I'm saying is that if you have a new physics that somehow generates this guy at low energies, and you try to measure deviations from using this theory, you will measure deviations for that type of new physics just as much using this thing as if you had put this guy here. You don't have to put them both. You just need one. Because at low energies, the effect of this guy and the effect of this guy really cannot be differentiated. So one of the things that might be of interest is to see how it works at the diagrammatic level. This is the second part of this calculation. And instead of showing the equivalence of this thing, what I'm going to do is add to my theory this guy, and I remind you this whole object here is is precisely this, the equations of motion, if you wish, the variation of the light theory with respect to phi. This is this. So if the theory is correct, then if the theorem is correct, then changing this, adding this, should not affect an observable, any observable. So I'm going to do and see, check whether that's actually the case. And the headache in this calculation are the combinatorial factors. So this guy, at the level of Feynman graphs and Feynman vertices, has two types of vertices. Vertices that have 4 legs, like this guy together with these 4 legs, and vertex that has 6 legs. The vertex that has 4 legs have a derivative. And so what you get is this 6i over lambda squared times the summation. The summation is over the 4 legs. I goes from 1, 2, 3, 4. And m squared is this m squared, and so on. And the operator O here has a term that goes like 5 to the 6. This gives this object here with this particular combinatorial factor of 5 factorial c over lambda squared. So what I've done is I've added to the tree-level Lagrangian, the renormalizable Lagrangian, I've added c over capital lambda squared times O. I've just added it. And so you have a theory that has these additional vertices. All right. So what I'm going to look is at the effect of having a single insertion of O, according to what I've told you, that should give no observable effect, on a process that has 6 external legs. Okay? External legs. So sample diagrams are this guy that comes from here, and a guy that looks like this with all possible combination of where the legs go. Okay, I didn't write down all these things. This vertex here is the vertex in the original renormalizable Lagrangian. This vertex here in blue is the horrible thing that I showed you before with the momenta and the blah, 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 and the factor of 6 and all those things. And what do you have? Well, this guy, what do you have? This guy here is, okay, let me first go there. Oh, this guy gives me this term here. I over 120 c lambda squared. 120 is 5 factorial. So from this guy, I get this. From these guys, I get several terms. Okay? One of them has a single particle pole, like you can see here and here, external. And another term that does not have such a pole. It looks like it is. The p squared minus m squared is, I got confused. Okay. Okay. So yeah. There's one term here. Okay, sorry. I'm sorry. I apologize. I need to have to be moving back and forth. It doesn't. Yeah, I'm just going to make it a little bit smaller so that it fits in the screen like this. Okay. All right. So analyzing Feynman graphs is always very boring, but I think it's a kind of an exercise that might be worth for you to look at. This guy has 4 terms, where k squared minus m squared correspond to each of the 4 legs here, right? When you look at this type of object, there will be one term of this 4 where the k squared minus m squared corresponds to this leg here. And I've labeled the momentum here p. So that term will give me a 6i over lambda squared, p squared minus m squared. And then there's a combinatorial factor. And then there's the propagator here, I over p squared minus m squared. And then there's that minus I lambda that comes from this guy. This is this term. And then there are other terms where the k squared minus m squared corresponds to this leg, and that leg. This is this guy, or these are these guys. Okay? Okay, so now what happens? You are now to take all particles on shell. These guys all vanish because on shell, the momentum on the particle here is squared, will be m squared. So these guys go away, And these guys cancel. And the headache in the calculation is getting this factor of 20 from doing the combinatorics. I have an explanation here, but in my experience, trying to explain combinatorics is a futile exercise. It kills everybody, and in the end, everybody understands combinatorics and his or her own peculiar way of understanding how things arrange themselves. And so the way I try to understand it is different, considering this field chi and trying to see how many ways I can contract this phi cubed times box plus m squared phi, which corresponds to, phi cubed box plus m squared phi. This would be what I call chi. How many ways I can contract this with a phi to the 4 vertex. And this is the thing that I kind of got, and I got the 20. But I'm happy to work with you individually if you're really curious about this thing. I think that this is less interesting to me than seeing how the things arrange by themselves, apparently miraculously, so that a contribution from this graph will cancel the contribution from the other graph, while the other contributions from this guy vanish on shell. And so you never get, you get no effect, at least for this particular example, of the insertion of my operator O in a process that has 6 external legs that are on shell. Let me point out that if the legs are not on shell, then these guys do not go away, and you get something. It's something that depends on the coefficient of the operator that I forgot to write down here, but it should go here, C. Okay. You can see this by, there's a lambda squared. I forgot a C here too. But on shell, that term disappears. And so the effective action will simply be independent of this operator O. And you can see this. The virtue of doing it, as in the previous slide, is that you have a general proof. You don't have to do diagram by diagram and calculate the combinatorial factors, which are always rather painful. Any questions? Okay. So the equivalence theorem allows you to eliminate operators. You had an example of how it works in quantum mechanics. You have a sketch of a proof of how it works in quantum field theory, and you have an example of how it works in practice at the diagrammatic level. So I think that's pretty convincing evidence that this is something that's reliable. Sorry, going the wrong way. And now I'm supposed to put it. I can even do this. All right. Okay. And that is the end of this. Any questions? No? Going once? Going twice? Oh, it's all gone. Okay. I'm back. All right. So let me just talk a little, begin. I'm not going to do much. I'm going to finish a little bit early today. I think that's enough formalism for one day. But let me just talk a little bit about the renormalization and renormalization effects of doing this. I am going to talk about renormalization of effective theories. I'm going to argue here finally that something I told you on the very first lecture is true, that the effective field theory in its infinity of coefficients is in fact a renormalizable theory. I will argue that the hierarchy that I imposed using this index is in fact something that's preserved under radiative corrections. That is, if you have leading operators renormalize themselves to leading order. If you include, so in order to understand how the renormalization works of your effective theory to leading order, you don't need any of the subleading operators at all. They don't contribute to that. So that will be interesting, I think, and reassuring. There's one subtlety, but I will cover that. The one thing is whether you can, another question you might ask is whether you can calculate the renormalization group running of these coefficients, the effective coefficients, because it's fashionable. And the answer is absolutely yes. You can certainly write down the running of the effective operator coefficients. The question is, I think, more whether you should do that or not, in the sense that, well, you get anything really, really interesting. And in most cases, the answer is definitely not. No. Why? Because in reality, our current reality is that we are probing the very largest or most interesting standard model radiative correction effects. So there are a very small number of observables that are sensitive, that have been measured to sensitivity so high that we can probe beyond leading order. Okay. This excludes QCD because it's strongly coupled, but I'm thinking of a weakly coupled part, the electroweak part of the theory. So there's some observables associated with the Z boson, which has been so well measured, that you can start seeing deviations from two loops. But most of the observables we have are sensitive only to tree level. A few select ones are sensitive to one loop, all within the standard model. And one or two are sensitive to higher loops. So you might question, and I think rightfully, whether you start looking for radiative corrections, and renormalization group running is a radiative correction of effects that are produced by the effective theory. After all, we have not seen any inkling of the effective theory effects in data. We have only limits. We have no observation. So we know that if there is new physics, its effects are much smaller than the standard model at tree level for some observables, smaller than the standard model plus radiative corrections in the select observables that I mentioned that are very high precision observables. And so imagining that it will be really useful to calculate the full renormalization group running of an effective theory, I think might be premature, especially since you notice that I've had 59 operators that you're going to look at. That's a lot of loops, a lot of loops with a lot of indices and a lot of combinatorial factors that you have to worry about. And so what I will do here is certainly not evaluate the running, but try to argue for you that the running that you would get if you should want to do the calculation can be obtained by just limiting yourself to the dimension 6 operators of the standard model effective theory. You don't need the dimension 8 operators to the standard to find the leading expression. Okay? So that will be the goal of this section of the theory. So let's stop now. I know it's a little bit early, but I think, again, I don't want to start something when we're all a little bit tired and overwhelmed. And so let's begin fresh tomorrow morning on the renormalization part. Okay? Yes, sir.
Suppose I have a operator which is CP conserving operator.
Hold on. Wait. Please wait. Please wait. Thank you.
And let's say I have an operator O. Is a CP conserving operator.
Oh, so this operator?
Yes.
Which
O.
operator?
Let's
This?
say O.
Oh.
And is there ever possible that is equivalent operator O prime can be CP non-conserving?
That OP can be CP non-conserving.
Let O be CP conserving and O prime becomes CP non-conserving.
Yes, it could be, because the standard model has CP violating terms. So you could imagine that when you do this thing in the standard, but it will be very small, in fact, right? Because the standard model has one certainly CP violating phase, in the CKM matrix, tiny effect, and it has a potentially another one in the neutrino mixing matrix phase, right? And so when you calculate this type of thing, there will be, at least for some cases, for choices of phi, there will be some times where this thing involves the CKM matrix. And so the right-hand side will be CP violating, right? For that term. But so there will be a CP violating term. You told me, okay, it's your operator, this is CP conserving, and the only way this can be consistently true is if O prime has a CP violating piece. However, the CP violating piece will be small. Okay, it will be small. Other questions? Yes.
So, in this proof, we said that O and O prime, they will not be distinguishable at low energy effects.
Right.
But can you tell me the scale at which we will get distinguishable effects? Like at what powers we will start?
When
having-
exactly? So the question is, when can you start distinguishing them?
Yes.
Okay. Yeah. This can be distinguished if you are sensitive to the subleading operators. That is, you have enough sensitivity. If you bear with me and assume this refers to the standard model effective theory, this would be, say, dimension 6 operators, right? If you are sensitive to dimension 8 operators, then you would see a difference between this guy and that guy. So I cannot give you a number, like if you measure blah, 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 everything, blah, blah. No. The reason for that is that we don't know that we are sensitive to the dimension 6 operators because having seen no effect, we don't know what lambda, capital lambda is. We don't know the scale. So when we see that, I can tell you, if lambda is 3 TeV, that's the scale where we'll be able to start seeing deviations between O and O prime. Okay. Other question? Okay, you get 8 minutes extra of actually we get 8 minutes extra of T. Oh no!
So that A parameter can be a dimension full. Some quantity can be.
Could be.
So I mean A is a some O is some other dimension operator and O prime is.
The thing works. In practice, that's not useful actually, but yes, it could be. So
Thank
A
you.
could have dimensions amounts. Yeah.
Thank you.
7 minutes extra. Thank you. I will see you tomorrow.